lunch break. Our next speaker is Dr. Mark Riedl. He's a professor in the Georgia Tech School of Interactive Computing and associate director of the Georgia Tech Machine Learning Center. His research focuses on human-centered artificial intelligence, development of AI and machine learning technologies that understand and interact with human users, in more natural ways. His recent work is focused on story understanding and generation, computational creativity, explainable AI, and teaching virtual agents to behave safely. And with that, let's give him a warm welcome.
Right. Thank you so much. This has been a delightful day. I've learned so much from the earlier speakers. Thank you all for hanging in on the last final stretch after a long lunch break. Yeah, so I've rewritten this talk after every single other talk that's happened today, because I felt that in order to build off of that, the conversations that have been going on in the room. But let me talk a little bit about maybe why I'm here. Long time ago, I won't say when, I worked a lot on planning and reasoning for story generation systems. I like to say from at least this long time ago, I've been considering reasoning, planning in language space. But around 2005, I started getting into virtual characters and simulations, and the people that were giving me lots and lots of money wanted to really kind of be able to explain what those characters are doing, why those characters are doing. So I've been thinking about explainability and interpretability since around, well, so I guess for many years. From there, it got me into value alignment with reinforcement learning agents back in the days before large language models. But as AI actually started to work, right, more and more of this notion that we really are going to have to care about explanation and explainability. Did a lot with value alignment along the ways, did a lot of training with reinforcement learning of large language models, small language models. That was GPT-2. I like to say I got this, I would have beaten OpenAI if my paper didn't get rejected 3 times. But that's all in the past. But in 2020, of all this sort of work, right, started thinking about end users, people out in the real world who were not developers. And what did they need to be able to get from the AI systems to trust them, to understand, to use them effectively and efficiently? And so we started looking at human factors, human-computer interaction, and human-centered computing. And even as we went forward, continuing to work on language models, reasoning, planning, really kind of keeping the human user, the end user, the non-technical end user in mind. And initially, we discovered you could do lots of stuff to help people feel good about using technologies. But ultimately, I think where this is all kind of converging is we want human-centered perspectives on explainability and interpretability, but we also want to stay faithful to underlying mechanism. And these all lines of are starting to converge here. And when I was invited to give a talk here, my first thought was, I've got so many ideas, so much stuff that I'm working on right now that I can't talk about. But this really kind of allowed me to start bringing some thoughts together. So what I'm going to do is basically think out loud in front of you all, and hopefully I say some interesting things along the way. If not, there'll be pretty pictures. Okay. So I've thrown out this term, human-centered artificial intelligence, human-centered computing. What does it really mean? Is it a philosophy for how to chase down computing problems? Now, the easiest thing to say is that the human-centered AI puts the human in the center. But what does that really mean? It means actually starting with a user, starting with a person in mind that you want to assist. Understand what these people or this person's needs are, their wants, their desires, and then identify what the technological contributions are going to be in order to address those needs or those wants. So really the idea is design the algorithms to address those problems, think about the person and then the algorithms, as opposed to what, the thing that might get me kicked out of this room is, sometimes we get really excited about algorithms and we do the things that we know we can do. And then we try to retrofit them to people. Like, how are we actually going to use this out in the real world, right? We can kind of do things in the other way. And the important thing about this is that oftentimes you discover new problems that you never knew existed once you start working with people. And then you get to make new algorithms. And that to me is really exciting. In doing so, we have to recognize that technologies don't exist in a vacuum, but in rich, complex, and often social worlds. And it often requires us to think very critically about ourselves, how we like to approach problems, and sometimes put that on the back burner and to say, well, we shouldn't have a predisposition of how we should solve a problem. We should actually kind of go and chase the human data. But ultimately, in the end of the day, no matter what you do, it's not just about human evaluation, although I like to do that, but it's the question, are we enhancing the human condition at the end of the day, right? Okay, now we're talking about explainability, we're talking about interpretability, so there is a human-centered notion of explainability as well. And as Jonathan kind of said in the morning, right, a lot of it is focused on developers, right? We can do interpretation to ask interesting scientific questions. We can ask developers need to think about their models, determine if they're operating correctly, and then isolate and fix those causes. Now, developers are end users, right? So it's not necessarily correct to say that working with technologists is not human-centered. It is just one of many different types of users out there. It's ones that we understand really, really well, okay? Because it is us, right? For the most part. But there's a whole bunch of people who are not us. People who use phones, people who put cats on Roombas, people who sit in self-driving cars, right? Every day, people are interacting with AI systems, robotic systems. And so the question is, if you're not a developer and you're not there to find and fix problems in your models, in your systems, what the hell is it that we can give these end users in terms of explanations that help them build trust and rapport and comfort and use technology appropriately? Okay, and the big question mark there is because this is really kind of sometimes very hard to figure out, and it's not entirely clear. And actually, it's not one thing. Many different types of users, different classes of users, different classes of systems have very different needs. But we've been talking a lot with people of many different classes and types, and we can tell you a few things about what actionability is. And what actionability means is giving people explanations that they can actually use, right? What is actionable to end users? Well, end users are ultimately, they come to AI because they're trying to do something, right? People don't use AI for the sake of using AI. They're often incorporating into their life saying, I have a need, I have a want, I have a desire, and the AI is the tool that I think is going to get me there, right? So what are they trying to do? The first thing you have to do is address that, right? And the other thing to recognize is that life of these individuals, these users, does not end when they stop interacting with the system. Once they've gotten what they need from the AI system, they go then and apply it out in the real world. And noticing that the context is a lot longer than just one user and one AI, one interaction. So what we need to do is we need to deliver information that the user can use to make informed decisions about how to respond to the outputs of the AI system, and then take that forward into whatever it is that they're trying to do. And if you design, you should design with this in mind, instead of necessarily, saying I can make an algorithm because I can make an algorithm. Okay. So with that in mind, I started to try to kind of like characterize the space of explainability. And I have sort of two dimensions, and one is continuous up and down, and one is more binary. The implications of having human-centered is you must have something that's not human-centered. I call this algorithm-centered. But what this really means is these are the algorithms that we know that we can do that weren't necessarily designed because they meet a particular user's need. Versus human-centered, which are things that started with identifying specific users and specific needs, and then building out the technology from there. Up and down, I have grounding and mechanism, right? So how much do these techniques kind of faithfully draw from the things that we know are going on inside the AI systems? There's probably a bunch of things that you recognize up here, like SHAP and LIME and causal interpretability. Attention and trace characterization are going to be some of the things I'm going to talk about. And just because this is column, we should kind of think about some of the things we've heard about in this workshop, in terms of circuit visualization, actually very well grounded in mechanism, not perfectly, because you have to do some weird stuff with sparse encoders. And then chain of thought or externalized reasoning, which is actually more about running the agent and a little bit less we know a little bit less about exactly what's happening inside this chain of thoughts, right? Now, this leaves kind of an empty spot here. And what I'm going to try to do throughout the course of this talk is kind of drive up into that spot, and I will kind of introduce some of my work that I think actually kind of fits in there particularly well. So I'm going to kind of work kind of through this space as we talk through the talk. Okay, so here's what I'm going to do. We're going to talk about reasoning with language. We're going to talk about explaining reasoning in a human-centered way and non-human-centered ways. Then we're going to try to make that faithfully attached to mechanism. And then we'll try to kind of draw some broader conclusions about language models along the way. Since this is a workshop on reasoning and explanation, and I wasn't sure if it was reasoning with explanation or explanations with reasoning, is it the and really an or? Doesn't English do that sometimes? Right. I thought I'd really kind of start out with this, and I think nothing I'm going to say is controversial for this particular audience, but I mean, there are conversations that happen about what reasoning. So first of all, what do I mean by reasoning? This is the thing that probably is controversial. I will say that reasoning is exploration of some potential space of action, particularly exploring the implications and the consequences of action. I think maybe I thought about this too much, but basically every time I come down to what is reasoning, there's a problem that has to be solved. There's many potential ways of moving through the set of actions, and we need to think about through some or many of those to kind of come up with a good answer. So to me, reasoning is exploration of some sort of space. Okay, now that exploration can be characterized in many different ways. It could be greedy, like my exploration is just literally go down one path and get to the answer, or it could be more systematic, where I look at many, many different options with a principled sort of way of working through all those different options. Okay, I don't really have a strong feeling about that. Some is more greedy, some is more systematic. Now, do large language models reason? I think there's kind of two ways we can answer that question. First, we know that there's evidence of anticipatory activations in parameter space. So parameters are getting ready for things that they have not produced yet. And there's all these little micro potentials and just kind of waiting for the next token to latch on. So in some sense, there is exploration going on in parameter space. I think that I've convinced myself that this is happening. And of course, more explicitly, we can train these things to do externalized reasoning or chain of thought, in which case they might literally actually kind of roll out some tokens, write more tokens about how they're backtracking, look at some other tokens, so we can actually kind of see them backtrack and look at different possibilities. So either one of these things, whether you're looking at implicit reasoning or explicit externalized reasoning, I think they are doing some of this. Now, I do think that either of these is a little bit closer to the greedy side. It may not be a necessarily issue, but you might kind of wonder what might happen if we were able to push language technologies, reasoning technologies more towards the systematic side. And there are technologies that allow us to do systematic exploration of behavior space. And it's called reinforcement learning. So this is going to get a little bit complicated because we use reinforcement learning in large language models often basically as fancy loss functions with gradient backtracking. But what they're actually kind of doing is they look at different rollouts and they try to identify different possibilities and reward some of those possibilities. That's at token space. We can also do it at behavior space, sentence space, or what is going on space, which is really kind of more what I'm going to talk about going forward. And this exploration could be done in pre-exploration, which is what we often like to do when we train large language models or build reinforcement learning systems. But it can also be done at inference time, and then we usually use the word planning when we do that. Okay, so now here's where things are going to get a little bit weird, because when we're talking about building reasoners that can reason about language problems, there's really kind of two different ways we can go about it. The way that we are most familiar with is to teach language models to be reasoners. Okay, so language models are not inherently necessarily reasoners, but we can teach them to do that. How do we do that? We can teach them to do more externalized reasoning. We can use post-training with verifiable rewards to get the language models to explore different parameter spaces and things like that. Okay, so that's what we're driving to. Many of us are driving to, but there's actually an alternative here, which is that if we already have reasoning technologies, maybe we can make these reasoners operate inside language space, right? And here we're talking about, I'm going to use the word state-space reinforcement learning just to distinguish this, but you might also say AlphaGo style reinforcement learning problems that are traditionally work in very discrete state spaces. But if we're going to get them to work in language space, you might ask, well, what is a state? When you're talking about all possible utterances of human language. And if you're doing that, well, how do you actually get a large language model into a reinforcement learning execution loop or training loop, right? So I'm going to spend a little bit of time talking about how we can build reasoners. Then I'm going to talk about how we can explain those reasoners, and then I'm going to talk about how we can make sure that those explanations are both human-centered and faithful to mechanism. Okay, so this is a weird way of thinking about language models, but basically putting language models into explorers, right? Okay, now we need an environment to do this in. We need a place where you can solve problems with language. And a few years ago, it was really hard to explain why we wanted to do language-based problem solving. Now I think we're all doing this. But basically, if you've ever solved a problem by going back and forth with someone on email, you solved a language-based problem. All right, so there is a type of benchmark task that also does this. Text adventure games, you think Zork, if you're born in the 80s. None of you look like you're born in the, oh, okay, all right. Two of us. Okay, I lie. I was not born in the 80s. I was born before the 80s. And anyways, all right. So what is a text adventure game? Well, it involves solving long horizon, high branching factor problems through actions expressed as language. Usually you have to express yourself in language. It's usually a simplified language, but it is language. And then you get environmental feedback in terms of text. It's chatting with ChatGPT in a systematic sort of way. If you're not familiar with text adventure games, the most famous one is called Zork. It is a fantasy game. You get little bits of information about what is going on in the world. You're able to perform actions in the world, like open the mailbox. You get feedback in terms of text. You can change the world, change your state in the world, or you can actually change the world itself, which allows you to do different sorts of things. And there's lots of common sense going on here, and there's some fantasy elements as well. Okay, so now text adventure games are kind of interesting benchmarks. They're actually kind of making a resurgence recently. Even the simplest games have about 200 billion actions per state. So that is actually harder than StarCraft, harder than Go. Requires causal reasoning and long horizon problem solving. Requires common sense reasoning in realish worlds. So even though there sometimes are monsters, there are also things like, what can you do when you open a window? It turns out that if you pre-train your agents on text games, they actually do better on robotics problems, which is kind of cool. But most importantly, they're hard. So Text Bench just came out here, and I'll just kind of point out one particular thing. How many games have been solved by GPT-5 or any of the frontier models? 0. No LLM has ever completed Zork or the 25 other games in here, and no deep AlphaGo style reinforcement learner has beaten any of these games either. All right, so if you're looking for interesting long horizon problem solving problems, you've got one now. All right, so how do humans do this? Well, it's hard for humans too. What do? They diagram the shit out of these things, right? To make sense of what's going on in these complicated worlds. We use a particular term in computer science. We call these knowledge graphs. I'm going to talk just about this just because I need to give you a mechanism so that we can eventually explain, right? We are going to track the subjects and relations between subjects and objects in these environments. You can sort of think about it as building an external memory. Play these games, we're going to use kind of a more or less classical reinforcement learning feedback loop. Here, where you get a game description information, you're going to construct a model, our knowledge graph, you're going to manipulate the model, you're going to think about what's going on in the state of the world as you understand it, and you're going to do some sort of actor-critic thing going on. Details are not particularly important here. The only reason this slide exists is because we called our system QBERT, and I just want to say, no one freaked out when I used the word Q star in a paper, but when OpenAI does it, everyone freaks out. Okay. All right. So how does this work? Where's the language model? I haven't talked about a little bit about language model. Well, the language model is taking the text, and this was BERT era. This is 2019, 2020 sort of things. I guess those are small models nowadays. But what BERT would do is basically try to understand what's going on in the environment, ask a lot of questions, construct a lot of factual information about what is going on in the world, building up a knowledge base about everything that's going on in the world, not just what it's seeing, and then attending to that and trying to make some sort of policy decision. And, we're going to do some text recurrence too, because this is kind of like our residual, right? Sometimes you just need the raw material coming in here. We slam all this into some sort of policy model. We try to learn that to perform action. Okay. Does it work? Yeah, we do better. Matter of fact, our technique holds state of the art on Zork right now, which means we can do about still less than a third of the game. Okay, and just on the side, you can also do value alignment with this. You can actually kind of give it examples of normative stories about normative behavior, and the system will actually kind of learn value systems as well, which is kind of cool. Okay, now, am I trying to talk you into doing it this way? No, I think we can go back and do it externalized reasoning with an LLM. We can do the teaching LLMs to do reasoning. That's fine. I'll tell you some of the reasons why you should or should not kind of do LLMs in a systematized execution loop. One is you get principled exploration. So that means you have certain guarantees that you can make over the quality of the plans or the reasoning that you get. That's kind of nice. We can operate in a high-level abstract space, so it can learn how to decompose a problem into the abstractions that are more like how humans think about problems. That's nice as well. The downside is reinforcement learning is still a lot about training on very specific tasks with very specific rewards. You really need to make more generalized model. You mean more diverse rewards and more diverse environments. This is a thing that we're starting to work on. And importantly, environments are not free. So there's a million startups right now saying we're going to build new environments to teach language models how to reason. Don't give them money. This is hard. They're building data generators, basically. So we're back to data problems. Okay, but perhaps reasoner models built like this are more explainable because they have this principled exploration technique. So if we do want to explain reasoning, maybe that's a reason why we use these techniques. Or at the end of the talk, we'll talk about how we can do LLMs without all this stuff. Okay, so what is it makes a good explanation for a reinforcement learning agent? I'll be honest, when I started to do this work, I didn't actually think about that. But we settled on two different things. We said, well, what about local explanations? What is the agent trying to do? What is it thinking about? Now we all know that opening the LLM black box is hard. That's why workshops like this exist. This is why conferences like this exist. I'm going to cheat a little bit. We have a knowledge graph, so we can use it as a surrogate for actually what's going on inside the black box. What's in your memory should be complementary to what it needs to learn policy, right? But we're also, in talking to users, we also had this intuition that what they really wanted was to know, what is the agent going to do next? Or why did the agent do the things it was going to do, depending on it, if you're talking about it as it's going on or post hoc, right? And so if reasoning is moving through action space, a state action space with respect to a goal, then maybe explanation should be in terms of characterizing that movement. So in other words, tell it how it learned to explore, what it's learned in that exploration. And in particular, we're going to talk about this in terms of sub-goals. So what are you trying to do? How does this action build to something that's more important going on? Very quickly, just kind of run through this. The technique's not very important. Attention's intention. We have a knowledge graph, so we can do attention over it. Right? So that basically tells us how much each observation or thing that it's thinking about is related to policy, i.e. what it will do, right? These are, in some sense, mechanistic, right? But I'm not going to spend a lot of time, because once you start spending a lot of time with attention, you start getting into a lot of debate, such as the paper, attention is not explanation, followed by months later, attention is not explanation, the latter being from Sarah Wigrefe, who's one of my former PhD students, who said, well, sometimes explanations are actually useful, or attention is actually useful in explanation. And then it gets really complicated from there. I'm actually kind of more interested in this characterization of traces, which really kind of starts to answer more of the why question. Like, why are you trying to climb a tree in this game? Why are you breaking that window, right? Why are you going north, right? And we ultimately want the agent to be able to say something like, well, I'm going north because I'm going to do this other thing later. And then at least that sense, the user comes away with a set of anticipation. Oh, okay, you're actually working on something. That thing seems relevant to your longer term goal. That must be good. So all this is a big complicated way of coming up with a probabilistic graph to kind of identify sub-goals in all the explorations that the agent does during exploration-based training, to get to the point where we can generate an explanation along those lines. I'm doing this because later I'm going to do that. Data, I'm not going to point too much to this data. What I will do is kind of point out this discrepancy between the attention-based and the characterization-based. Basically says that people are less satisfied when they don't get information that kind of tells you this is what the agent is driving towards, that there's some sort of goal-oriented notion to these agents. Okay, so they really want to know about the goals and how they're going to get to these goals. And that's what really was telling us. And that bounces back to the human-centered notions that we started out with, which is they're trying to do something. They're trying to understand the agent in some sort of larger context, and this is the information that was giving them more information. So we actually went and we talked to lots and lots of humans about what they wanted to do, and each one of these little boxes that you can't read is something that people said, like, this is what I wish AI systems would tell us. And almost none of it is attention or circuits. There's a whole bunch of things on here, but I really want to point out the three things that humans are really telling us, which is that to them, action could be mental space. So like reflecting on information, making a decision, or choosing trust is action to people. They wanted to interact with the XI system in multiple rounds, in multiple phases. And then what ultimately they want to do is they want to do things like change the inputs to steer the agent's behavior. They wanted to contest the results. If they didn't like that, how do I take this information and sue someone, for example? Sometimes it was like, I want to use this information, I want to take it, and I'm going to talk to someone else. To them, that was explainability. It's an explanation that helps people figure out who to talk to, was useful. Or raise an issue with the developer, identify a bug. They're not going to fix the bugs, but they got to talk to someone about those bugs, right? So these are the sort of things that people are trying to do because their life, AI is just being invested into their lives. Now from that, right, we started thinking a lot about something called counterfactual explanations. And now Disney is going to sue me for copyright violation. What is a counterfactual explanation? It's basically asking an AI system, why didn't you choose a different action or a different label or a different behavior? Okay, so turns out counterfactual questions are really, really useful because they identify a mismatch between what the human thinks should have happened and what the AI thinks should have happened. But also, they're highly actionable in at least 3 different ways. If the user is mistaken and the AI is correct, we can help the user fix their mental model of how the problem should be solved. The user can contest it and can say, well, I actually wanted that counterfactual. I wanted to, have that happen instead. Why didn't that happen? Or I can actually start to steer the AI system saying, well, now that I know that there are different possible things that can be explored, and if I like those other things, now can I figure out how to make those things happen? Okay, back to reinforcement learning systems. And then I should say that at this point, I don't really care if it's a reinforcement learning system or a large language model, but what I do want is that there's some sort of multiple factorized rewards. And I think that's happening more and more with verifiable rewards, right? We're going to teach it some math, we're going to teach it some science, we're going to have different rewards playing out in post-training. Think about this as not a grid, but language space where there's only 4 words you can say and only 20 some different possible things you can talk about, right? If you want to think about it that way, but some things are good and some things that you talk about are bad, right? Here, stairs, this is, to me, it's an agent that can fall down the stairs or get stuck on a rug. Okay, so what is a policy? Whether it's an LLM or anything else, what we're trying to do is we're trying to estimate the utility of any possible state and any possible action in those states. One of the reasons why explanations are so hard, whether it's for language models or other agents, is that once we compute those utilities, like, and these are nested in our large language model, we throw that information out about how we got those utilities. At the end of the day, it was just like, hey, this action was better than the other one. This one got me more reward, whether it's a verifiable reward or whatever, than some other action, okay? And that means that when it comes to time to explanation, it's really hard to give explanations. We can give an explanation like action A was the best thing to do in state S because after 10,000 trials or 10,000 tokens, right, action A led to a higher reward than any other action. And this is not actionable, right? But this is often all we can say when we look at utility values, or we try to extract information from our models, right? So that's no good. But if we switch to the counterfactual reasoning, right, we get better questions and we get better answers. Like, why did you go north? I chose north because if I went south, I would fall down the stairs, right? So if north is the best thing I did, that implies there's something less good. And I'll tell you why I was losing reward as potentially actionable information. Right, what does that tell me? It's like, oh, I get it. You're afraid of stairs. I'm not afraid of stairs. I didn't realize robots were afraid of stairs. Okay, that's useful. Don't make my agent go near the stairs anymore, right? Or do something about the stairs. Okay, so those are actions, actionability. Okay, so how we're going to approach this, what we're going to ultimately try to do is we're going to try to tie those explanations, counterfactual explanations, to the rewards, to the reward function. Okay, so what we're going to do is we're basically going to learn how every possible state that we might pass through, and large language models will have, this will be harder, but I think you can still do it, and to predict what is how every possible state you can pass through is related to the different possible rewards. Think about it as training lots of models, each model trying to, oh, can we see? Yeah, okay. Trying to figure out how to make reward happen. So imagine an agent that's trying to learn not just how to get to the goal, but how to fall down the stairs, how to get stuck on the rug, and all these other things as well, right? If we had these different models, they would be able to tell us of all the different things you could do, these will get me towards certain states that are either really, really good or really, really bad. Now, to tie this to language, to be able to create those explanations, you don't just need the reward, but you also need language attached to the reward, and which we can do, right? We can say this state down here, the red state, actually has words like fall and stairs associated with it. So we should be able to talk about that and not just talk about numbers. And then all we have to do is I can look at the actual, what the policy really wants to do, and I can look at possible counterfactuals, and I can characterize the differences in terms of the influences, the reward influences, right? These traces give me more of this kind of reward, less of this kind of reward. What kind of reward did you actually want, right? It's sort of the way we're driving here. Again, aligning all the details here. Is this faithful? Well, it's pretty faithful, not 100%, pretty faithful. So if you have some sort of actual policy, and this is just an agent trying to move around grid space, and I guess squares are bad here, something that's going on, some complexity here. We can take all the different influences that we've learned through these separate influence predictor models, and if we basically multiply them all together, we can actually reconstruct the actual policy with about 90% accuracy. So these influences track pretty well what the agent is actually reasoning about or thinking about. So we've done this in lots of different environments, not just grid worlds, but Minecraft-like environments and things like that. And again, lots of information that I could give you about how well this is working. But basically, the point is when we looked at lots of different ways of digging into reinforcement learning policies, our system was found to be most useful. And again, this was a lot about understanding how the agent was thinking about the environment itself. What does it react to? Why does it react to it? Why does it think zombies are bad and why it should move away from zombies? So we did a lot of qualitative analysis to figure out why people found this to be more useful. And it was helping them build better mental models of how the agent interacts with the world itself. People were learning to approximate the policy underlying the model. And I think that's pretty powerful, right? Because if we understand how our technology is working, we will use it correctly more often. Also, we can intervene in the system. So as we have an agent that's working through its particular state space, and the agent saying, well, this is how I learned how to do this sort of thing, the user can come back and say, well, you know what, I really wanted you to do something else. I really wanted you to do, I wanted you to solve the problem, yes, but I want to solve it in a completely different way, right? The agent should be able to come back and say, well, you know what, if you wanted that, let me help you figure out how to make that counterfactual actually happen. You should have made the world look like this. And then the user can say, all right, well, now I can at least start thinking about how I can change the environment, change the initial conditions, change the inputs to get the behavior that I actually wanted out of this. Basically, the AI system can teach the human how to control it, how to steer it. And I think this is a very powerful use for explanations. I'm going to skip over the details. The details are world models. So I'm trying to just throw as many buzzwords in here as I can. We got, see what we got. We got memory, we got world models, we have interpretability, explainability, reasoning, planning. Did you get them all? Okay. All right. All right. All right. Let me kind of start to wrap up with some sort of conclusions. All right. So actionable explanations focus on behavior of the agent with respect to users' needs. Now, if we're thinking about reasoning agents, right, we want to explain how agents came up with the solutions they get. In this case, it's agents moving through the environment, but I think this could be lots of different things. The basic underlying premise here is that we want to explain the behavior with respect to how they explored, right? The exploration was how it sorted through all the combinations to decide which is the right one. or the best one that it thought. Right. And then counterfactuals, I think, are very, very nice in terms of actionability for people who are non-technical, because it also allows them to start exploring some of these paths not taken and understand why those were not taken. And I think that is key to basically, basically through process of elimination, find out why the agent was doing the thing it's actually doing by looking at the different possible alternatives and why they were eliminated. Okay. And again, I think we're starting to see evidence that once you have that mental model, by looking at how the agent explored and came up with certain decisions, and building a mental model about that, then you can also start to understand how to influence the model itself to get the outputs that you actually want. Better AI usage, basically. Now, haven't talked a lot about LLMs in a while, right? The last project, we actually threw the LLMs out and said, well, let's just focus purely on the exploration mechanism. We didn't have to do that. We just did that. As we move to post-training with reinforcement with verifiable rewards, we're already seeing that agents built with multiple rewards are there. So we have the multi-factorized rewards. We tend to just like add them all together, which is kind of not the right thing to do. But if we keep these rewards separately, I think we can start to even think about complex language spaces from large language models in terms of following how the reward flows through what the agent is trying to do. What, in particular, as it generates chain of thought, some aspects of those chains will be more relevant to certain rewards and other rewards. And we might want to start characterizing those chains of thought in terms of the rewards or the reward potential that every single token is giving you, right? Now, I think that does kind of lead to some bigger questions like, what is a state, right? If we're just talking about chain of thought agents and reasoner models, should we be talking about reward at the token level, at the sentence level? Often we care about reasoning models because they're talking about actions that can be executed either through APIs or we execute what the AIs tell us to do. Right, so sentence level might be the right thing to do, or some sort of abstract notion of state and action. And if we are interested in abstractions, there are lots of different ways that we can extract discrete state approximations that are above the token level. And I'll let you kind of read those if you're kind of interested in them. But basically, we can kind of build state spaces that look more like what humans are thinking about, which I think should be helpful, because if we can track between, if AI systems are kind of building out human-like thought structures, then we should be able to explain in terms of the thought structures a little bit differently. Okay, so wrapping up, okay, we want agents. We want AI systems that do stuff. These are our reasoner agents. These are our planning agents, okay? Language models, they can be taught to reason. We're doing that now. Lots of exciting stuff that's happening at Colm, even this particular week. But we should also recognize that there are many other ways of doing this. For example, we can build on top of existing reasoning models and making them work more like LLMs. So we want LLMs that work like reasoners, or we want reasoners to look like LLMs. I don't know. Ultimately, the future will decide which is the right bet to make there. But ultimately, if we're putting technology in the hands of non-technical users, which it seems like we are doing, right, we really have to ask, what is the user doing? How do we know what they're doing? In the context of what they're doing, what is going to be actionable? What is it that they need from our AI agents in order to go into the next steps of their life after they step away from the AI, after they step away from the technology? What are they trying to do? Even who is the user, right? It makes a big difference in terms of what they're trying to do. Factoring all this in to our explanation systems is probably going to make these systems friendlier, more usable. But I do want to remember that even as we look at actionability and human factors and human-centeredness, that doesn't mean we have to abandon our goals of mechanism and tying our explanations to mechanism. Matter of fact, I would argue that we want both actionable, human-centered, and mechanistic. And I do think that we can achieve that. I think I've taken a few tiny little steps here, but I think there's a lot more to be done, and there's a lot of very exciting questions to be answered there. And ultimately, reasoning is about the future, right? What is going to happen? What is the next step in action? What is 3 steps in the future going to do? Where do we get our reward? How do we achieve our goals? Right? It's about future states. It's about exploration. And so explanations themselves, to the extent that they can be made about those goals, future states, and explorations, are going to be things that we can deliver to non-technical users and have practical value and provide practical value towards those end users. Okay, thank you all for being here after lunch. I also want to thank some of the people who put a lot of work into this. If you thought all of this was weird, I just want to point out that all these people are successfully employed after being weird with me. Many of them are faculty now. Some of them are actually at this conference. You might have run into them earlier this week. And if you do think this notion of explainability and human-centeredness is interesting, and you think Montreal is cold, you can come down to Atlanta where it's not cold. And in a few weeks, we'll be talking a lot more about how to make build safe, responsible systems for real world end users. With that, happy to answer any questions or entertain blank stares. Thank you very much. Shouldn't have said blank stares. Okay, yeah. Say that one more time for the people online.
So I was wondering if you heard about David Chalmers' ideas on propositional interpretability, and how that relates to kind of human-centered explainability, and if you think that we should try to describe basically LLMs as having attitudes toward propositions, so like beliefs, desires, etc.
Yeah, I don't know Chalmers' specific work on that. I know a lot of his work on understanding and what understanding means. So I think there are ultimately, a lot of ways to think about explanation, and I've only kind of touched on a little bit here. But if we look back at sort of the landscape, and we might ask, how is it possible that we can have things that are not grounded in mechanism that are human-centered, i.e., and actually meet needs? And some of these things on the bottom here are the work from some of my students who said, you know what, we will build systems that can produce explanations with no guarantee of faithfulness to mechanism instead. But when we run human subject studies, people derive value and actually execute on tasks better with the AI providing explanations in particular ways. What that tells me is that when you focus on need, the need doesn't necessarily mean faithfulness or mechanistic is necessary. So if the need is met by attributing belief states or desire states to an LLM, and that helps the user execute downstream on whatever they're trying to do more accurately, then that is a perfectly acceptable way of going about explanation and interpretation. A lie that's useful is still useful in some ways, right? Yeah, so I guess I'll just kind of leave it there. Now, I think you do run the risk of that lie being taken too far, and we have issues with sycophancy and like anthropomorphization. And so I would kind of also say, like, you also, I think, have to look at the side effects of these things as well. And I think actually not many people are looking at the side effects or the dark patterns of explainability.
And then do you think there's any, so you're kind of in your answer, you're a little bit assuming that they're not going to be faithful, or you said that high chance that they're not going to be faithful. Do you think there's any chance?
Oh, yeah. I implicitly made the notion that AI LMs don't have belief states. No, actually, I kind of do think they have belief states, but I think it's about the presentational aspects, right? I think here's another, okay, so this is, I'm being recorded, awesome. So there's a lot of power in explainable AI to de-anthropomorphize, right? When I start breaking it down into mechanism, like if I start saying, here's a circuit, right? I'm totally going to ruin your suspension of disbelief that this is a real human, because people probably don't have circuits. And I mean, neuroscientists will probably disagree. But, as I sort of attach it to mechanism, it does make AI systems more likely to look mechanistic, like mechanism, right? So I think you can provide a service, provide a value, break anthropomorphization at the same time, which might then allay some of these kind of things that we're hearing about in the news. But I think you could also do it with anthropomorphization too. We can talk about the biology of an LLM as if it's a human brain, right? These are just different paths and different philosophies. And I think we do have to look at, put these things in front of humans and actually kind of run human subject studies and say like, what is really changing in the mental model of the user? And do we want those changes or do we not want those changes? So get a little bit philosophical here, but an awesome, amazing question. Thank you. Okay. Let's go.
Yeah, thanks for the nice talk. One kind of connection that comes to mind here with faithfulness is, you know, let's say the trendy rebranding of that is things like chain of thought monitoring, like trying to determine if systems are being deceitful or something like that. And one other connection that I see here is like you're talking about reasoning as search, which I 100% agree with, and I think we see made a little bit more explicit in some of the long chain of thought models that explicitly have notions of backtracking. So there's two concepts, I guess. Is there some way that those kind of, you see a connection between that and what you talked about here? Does this stuff sort of port over there? Or are there different?
Yeah.
Different?
No, that's great. And again, these are thoughts that I'm still toying with, right? But there's a reason why I put chain of thought next to the trace characterization. Because I think they're doing very similar things. They're running the policy, and then we look at the policy and say, hey, something's going on here. Right. Now in my RL agents, they have one goal, so they don't get particularly confused, and you know, we kind of know what's going on in the policy. With chain of thought, like you can sort of think about as like many minds all kind of mushed together, right? And then sometimes they go off in lots of weird different sorts of ways. Right. But at the end of the day, it is the policy, the LLM itself as a policy is like putting out tokens. And sometimes those tokens are relevant, and sometimes the policy is saying put out things that are not relevant to this. I think because it really kind of doesn't know. You know, it's maybe over exploring or something like that. I'm not entirely sure. Where the hell was I going with this question? But I think, you know, to look at an LLM as a policy and say it produced this chain of thought because it thought these were the right tokens or the right sentences to produce. We have to go a little bit further and say, and we've seen lots of things that say chain of thought is really not always very faithful. Right? And sometimes I think it was your talk where you said, you know, figures out the question and then says, oh, now I got to talk for another 5 minutes, right? And put out tokens that are irrelevant, right? So at the end of the day, if we really want to know anything, what chain of thought is telling us, we should really kind of understand why the policy produced those tokens. And that means I think we do have to trace those back a little bit more. So I think we do need to dig somehow into those chains of thought and tie those things to mechanism. I'm proposing reward as a way of saying, well, tokens are generated because some sort of post-training happened. So we should know how that post-training is affecting those chains. But there are other ways too. Maybe you can trace them back to the circuits, right? There's a second part of your question about, anyways, I'll stop there because I'm long-winded. I think there was one more question. Do we have time? I'm in charge now. Okay.
Yeah, I'll be quick, and this is a very high-level question. I really like the idea of actionability, because with explanations, it's always like, why are we even explaining what's the point? And this feels like a really good one. But my question is, are you thinking of actionability as something that we can actually model and optimize towards? Because then we go in a whole human AI, almost like a modeling the system together. And then you can think about, if I do this, what can the human do? And then you can have mathematical notions of empowerment come in. But that also feels like a slippery slope, because modeling the human is a slippery slope. Or are you thinking of it more as a question we can ask ourselves when we're designing the kind of explanation that we think about?
I mean, at the level that we've been working on, it is the question that developers should be asking ourselves. And I think, you know, a slide that I cut was how you can design evaluations around the notion of actionability so that you know that you're at least evaluating the correct things. Because we have lots of experiments, especially in the human computer interaction community, that says like explanations and interpretations are not actually helping people. And in some sense, it's because they weren't designed to help people. All right. But if we're evaluating the right things, then we build the right things. Right. And if we build the right things, then we get the effects that we actually want. So at a minimum, we should think about actionability as design targets or evaluation targets or benchmarks, or if you want to think about those terms. Or now, should we train them to be actionable? Maybe. I mean, I think you'd run the risk like, you know, are you over specializing to a particular type of action, or do you need to address all actions? In which case you need to know what is the user trying to do. But on one hand, it's like maybe the AI should actually learn to ask what the user are actually trying to do and why they want to do it, and then downstream figure out what the actionability is. So could we build rewards around that? Verifiable rewards, maybe even? Yes, but I don't know how you would get that data, but that's a different issue. But you know, at the end of the day, like AI, to the extent that AI systems have theory of mind about their users, I think that's a very powerful concept. And I think it's a problem, it's something that is people are starting to think about, but I think a lot more thought could be put in, but we're sort of getting away from the questions of the explanations at this point. But great question, thank you.
I think that's all for session.
All right. Thank you all for your attention and the great questions and conversation. I hope we keep the discussion going. Thank you very much.
Yep, and up next we have Jen Workman Bong for virtual class challenges.